All right, we're going to be checking to see whether or not this sequence converges. The way we test convergence is we take the limit of the sequence, we take the limit of a sub n as n approaches infinity. We're going to do that for our sequence over here, sine of pi over 2 plus 1 over n. So let's take this limit. Limit as n approaches infinity of sine of pi divided by 2 plus 1 over n. Now, the way we approach the other problem is very similar to how we're going to approach this one. Let's look at the only thing that involves n in this sequence. That would be just this portion right here, right? What does this approach as n approaches infinity? 0, correct? I will put in plus 0. So we have the limit as n approaches infinity of sine of the quantity pi over 2. Let me fix that. Plus 0, which would be sine pi over 2, which, as we discussed earlier, equals 1. So yes, it converges to 1. 1 second, Caitlin. No, I did not plug in a random number. The only portion we're looking at that involves n, look up here. We're interested in when n approaches infinity. None of this portion has n, well, except for sine, but that's not the same n, obviously. We're looking at this here. As this approaches infinity, that goes to 0. We're looking at just the limit of 1 over n as n approaches infinity. And that equals 0. Caitlin, you had a question.
So you can actually separate it?
I'm just evaluating just this portion. I'm thinking about what happens to this as n approaches infinity. Because is this affected by n at all? No, it is not. It's only affected by this portion right here. So I'm evaluating just that portion of it. And though, yes, you guys are right. I heard you guys talking about sine oscillating, not sine of a constant value. Sine of pi over 2 is a constant value. If you had a variable, then yes, it would oscillate and it would not exist. But like we said, sine of pi over 2 is just 1. So yes, it converges to 1. Any questions? Excellent. Now, when we evaluate the limit here, we're trying to see whether or not this converges. The way we do this, we take the limit of n over 2 to the n as n approaches infinity, right? You could approach this problem many, many different ways. You could use L'Hopital's rule because it's both infinity over infinity, but I don't think it's really helping out many of you because I don't think all of us know the derivative of 2 to the n. Would not help us out. An easier way of thinking about it is thinking about rates of change, thinking about actual values of our sequence. What grows faster here, n or 2 to the n? Thank you, Olivia. Yes, it is 2 to the n. 2 to the n grows much, much faster. Anything that is an exponential equation grows very, very quickly, like very, very quickly. Really, anything's going to grow faster than n besides a constant. So this is an example of a bottom-heavy problem. Shout out to my pairs. Bottom-heavy. When we have a bottom-heavy function, and then, Caitlin, this is what you were talking about. When the bottom grows more quickly than the top, the limit approaches 0. It converges, yes, to 0. Yeah, maybe, I don't know. All right, now we're going to be checking the convergence of this series. A sub n equals the natural log of n minus the natural log of n plus 1. The way we do this is we're going to be using and applying some of our properties of natural logs. Obviously, we have to take the limit as n approaches infinity. This would give us natural log of n minus natural log of n plus 1. Now, as we evaluate these as we go to infinity, both of these grow without bound to infinity. Both of these grow without bound to infinity. That's not really going to help us out. Because infinity minus infinity does not equal 0. Or does not always equal 0. This is a property of infinity. It is not a number. It does not have the laws and rules of real numbers. So what we're going to do is we're going to actually combine these. How do we combine the difference between natural logs? It becomes a division or a quotient. The natural log, and now I'll put in my parentheses, n divided by n plus 1. The limit. No, we're not really factoring here. We're combining. We're using the properties of logs, which says the difference of logs will be a quotient. Now, just like we did with the sine one before, all I'm really interested in is evaluating this inside portion. Let's see what this goes to. What is the limit? What is the limit of n over n plus 1 as n approaches infinity? No, it approaches 1, right? Largest on the top is n, largest on the bottom is n. You could also use L'Hopital's rule here as well, but it's just n over n, which equals 1. So what we're evaluating here is the natural log of 1, which is, it is indeed 0. So our answer here is yes, it converges to 0. Yes, it converges to 0.